In this lecture, we're going to talk about the effects of short T2s on the profiles that are excited by an RF pulse. Then we're going to talk about RF pulses for UTE sequences, that is half pulses, and RF pulses for suppressing long T2 signal components. So let's first look at the effects of T2 decay during excitation, and we're going to be considering here the small tip angle case. So we can do a little graphical derivation here. Here's the RF pulse that we're going to play out, and here's the gradient. And let's look at one instant in time where the RF pulse knocks down a little bit of magnetization that is proportional to gamma b1 of tau, this time point, d tau, which is the incremental width of the time point. This magnetization is going to be knocked down right here at this time point tau, and then it's going to experience T2 decay up to the observation point t. So we have a small increment in mxy that is excited at time tau. It decays with rate 1 over t2 up to the time t, and it also precesses according to the remaining gradient area up to that time t. And so the phase that it accrues is equal to e to the I2 pi k tau comma t times z. Okay, so the overall incremental mxy is given by this expression, right? Multiplying all these terms together. And we can integrate this then through the entire RF pulse up to this time point t and obtain this expression. So this is the same thing but just integrated over the entire time duration. So again, what we end up with then is the same thing as a small tip approximation expression, but we have this additional T2 weighting. So what we have overall is a Fourier transform of an exponentially weighted RF pulse. So here's the applied RF waveform, and here's the effective RF waveform given this T2 relaxation. So what we have is essentially that the time points early on in the pulse are going to decay more than the time points later in the pulse, since the magnetization knockdown here won't experience as much T2 decay as magnetization knockdown here will. So we'll have this kind of squishing of the RF pulse earlier in time that decays as you move on throughout the pulse's duration. So then the primary effect of this is loss of signal, and the secondary effect is going to be loss of sensitivity. And on the next two slides, I'll show an example of this. But first, let's look at echo time in a gradient recalled sequence. So the echo time of a gradient recalled sequence is generally defined as the delay from the center of the RF pulse, that is here, this dashed line, to the k-space origin in the readout. Okay, and then I'll label all these different axes here. So we have the RF pulse plotted here, the gradients, the slice or z gradient plotted here, the y gradient, which is we usually denote as the blipped gradient, and gx is the frequency encoding gradient denoted on the last line. So if we want to minimize T2 decay, we would want to minimize TE, right? So that we could look at very short T2 signal components. So in order to do that, we'd ideally like to eliminate all the stuff that's happening between the dashed lines here in order to achieve a zero echo time. So two ways to do this are to use half pulse excitations and radial readouts. And we're going to go into more detail here then on the half pulse excitations. Radial readouts are center out radial readouts are readouts that start at DC in k-space and move out along a radial line. And since you start at 0, you don't have to do any gradient encoding before you start sampling, hence they're a good choice for ultra-short echo time imaging. So here's a simulated example of the effect of T2 on small tip angle excitation. Here's an RF pulse, a time bandwidth 4 applied RF pulse, and here's the effective RF pulse that's played out when we account for a T2 of 2 milliseconds. So you can see that the RF pulse is more squished at the beginning. It's a little bit hard to tell, but overall this trough is more squished than this trough. At the beginning of the pulse is more squished than it is at the end of the pulse. And this overall results in a loss of signal for the most part. There will also be some blurring if the RF pulse is longer. Okay, so let's talk about a half pulse short T2 imaging pulse sequence. So what we do here is we play out half an RF pulse, and we acquire signal twice. So we acquire it once with a positive gradient, and the second time with a negative Z gradient. So what we have here is a half pulse excitation. We're assuming here the use of a symmetric RF pulse in time. And so we take half of that symmetric RF pulse, we play it out twice, and then we take those two acquisitions and combine them. And they are combined with opposite gradient blips, opposite Z gradients. Polarities. And here is illustrating a radial readout on the X and Y axes. Okay? So let's look a bit more closely at how and why this half pulse excitation works. So here's the first excitation. We play out half the pulse with a positive Z gradient. And what happens here is that we're moving from the left side of K-space to DC throughout the duration of this pulse, and then we stop at DC. Conversely, for excitation 2, remember again that the instantaneous excitation K-space location is the integral of the remainder of the gradient. So that means we start at the other side of K-space, of KZ space, and move to the center as well. Both pulses start on one side and move to the center. And so that is, assuming linearity here in the small tip angle regime, the sum of the two acquisitions will be the same as a conventional slice selective pulse. So that is, the linearity of the excitation extends all the way into the signal, and so we can essentially synthesize this linear excitation by summing the two signals together from two consecutive acquisitions, such that we obtain the signal corresponding to a full pulse excitation. A radial readout for short TE imaging would start at the origin of K-space and then go directly out. Right? So you'd be tracing this you'd be collecting data in a circular support in K-space, and the echo time would be here at DC, and you would scan out with every acquisition. Here's a practical pulse sequence to implement a half pulse excitation with a radial readout. And you can see we have a half pulse excitation here. It's smoothed a little bit because we have to sample on the ramps. So this is ramp sampled RF. We can't waste any time, but we also can't just instantly switch the gradients to 0. We have to let them ramp down to 0. So there's the slice select gradient, and then we have the trapezoids for the radial readout. Now the problem with the short T2 pulse sequence is that everything shows up because we're exciting two slices, because we're doing the half pulse excitation. The images also show proton density only because there's usually no T1 weighting or other kinds of weighting, and it can be hard to tell what has short T2s. And so then we really need to somehow look at ways to improve the short T2 contrast. Okay, so we have a few options here to get short T2 contrast. We can first of all collect a second image with with a longer echo time, and then compute the difference between these two images to subtract out the long T2 components. So then, because the long T2 components will stick around in both images, subtracting these two images should leave behind only the short T2 components. Problems with this are that the second image only adds noise to the short T2 voxels, and inhomogeneity, or delta B0 in a voxel, will look like short T2 because of dispersion through the sequence. That is, if you extend the echo time, not only are you going to get the short T2 signals decaying away, but also longer T2 components with lots of off-resonance through a voxel will also decay away, and they'll be confused with short T2. You can also exploit T1 differences between tissues that generally have short T2s or long T2s. That is, tissues, not solids, with short T2s tend to also have short T1s. So an RF spoiled short TR sequence will show short T1s and emphasize short T2s. The problem is, though, that it's still not T2 selective unless it's combined with the first step here. And the third option we'll go into in a bit more detail here, which is to exploit the excitation differences, the different excitation properties between long and short T2 components. That is, this is kind of taking the previous problem that we illustrated about T2 effects on RF pulses and turning it on its head to take it to our advantage. That is, T2 affects our ability to excite or invert magnetization, which is usually a problem, but we can exploit this using pre-pulses to establish short T2 contrast. Okay, so here's the basic idea of long T2 suppression pulses. So the basic idea is that excitation and relaxation are competing processes. Excitation creates MXY and relaxation destroys it. So, graphically, we can think of these two competing processes as we have for excitation an RF pulse vector here knocking magnetization towards the transverse plane. But for the purposes of this problem, we can think about the T2 relaxation, which is pulling it as a process which is pulling it back towards the z-axis. So both are effectively rotation rates in the small tip angle regime. Now, if the strength of the RF pulse is much, much bigger than T2, then magnetization will be rotated away from the plus z-axis before it is destroyed. On the other hand, if the strength of the RF is much, much less than T2, then no MXY will be created and the magnetization will stay untouched along the plus z-axis. So we can exploit this by playing out a long T2 suppression pulse. This is a long pulse with a low amplitude. It's a 90-degree flip angle. And if we denote T as the pulse length, then then components with T2s much, much shorter than the duration of the pulse are not going to be excited. And the components with T2s that are much, much longer than the duration of the pulse are completely excited. Then the excited MXY that we produce with this suppression pulse is dephased or crushed by placing a gradient after the pulse ends. And the remaining magnetization components which correspond to the short T2s will be imaged with a short T2 pulse sequence, and the long T2s will not show up. Okay, so here's the pulse sequence. We have the pi/2 long low amplitude 90 pulse. Then we have the crusher immediately following it. Then we do our half pulse sequence that I illustrated before. So what's happening here vector-wise? So we'll illustrate here what's happening to a magnetization vector for a long T2 component and then for a short T2 component. So at equilibrium, the long T2 component will be pointing along Z. Then the RF pulse will excite it down to the transverse plane, where it will dephase, right, in the transverse plane, due to the gradient crusher. Then, that is, it will be excited and immediately dephased, such that it cannot recover and produce signal in the subsequent excitation and readout. On the other hand, the short T2s are going to be along the z-axis. They won't really be changed by the excitation pulse, and so that they also cannot be dephased. And so they won't be excited or dephased at all, and they'll still be there to be imaged with the half pulse sequence. Okay, so let's look mathematically at the long T2 suppression response. Here's the Bloch equation that governs the rotation of the magnetization, the behavior of the magnetization during the pi/2 pulse. This is like the Bloch equation that we've seen earlier for RF pulses, but we now have the T2 relaxation terms on the diagonal. Now the last two equations will decouple from the first equation, right? The MX equation doesn't depend on the MY or MZ components, so we can look at these in isolation. And we'll write these as a single equation in MZ. So you can solve these out, you can substitute out for Y and get a single equation in MZ. This corresponds then to a linear, constant coefficient ordinary differential equation whose roots are given by this expression. And then we can subsequently solve this to get an expression for MZ during the pulse. Now for a pi/2 pulse, if the pulse length here is capital T, then we get that gamma times B1 should be pi/2T. That is the strength. That is the if we have a pi over 2 pulse, the amplitude is determined by the pulse duration. Setting t equals t in the above expression for mz, and setting gamma b1 as pi over 2 capital T, and simplifying a lot, we can arrive at this expression for the z magnetization as at the end of the RF pulse. So, and you can see here that this is a function of the ratio of the T2 and the RF pulse duration, and all other parameters are constant. So we'll look at an example of this on the next page, but for a given pulse length, capital T, what we find is that T2s that are less than capital T are preserved, while T2s that are greater than capital T are suppressed. So to preserve T2s of 2 milliseconds or less with 80% efficiency, we need a 20 millisecond long RF pulse. So here's a plot of MZ amplitude versus the ratio T2 over T. And you can see that when the ratio is 1, we have about a 70% or better suppression, almost 80% suppression. So here's see, these are some images. I apologize for the poor image quality, but looking at signals that are left over in different T2 pools for a very short T2 with no suppression versus longer T2s short T2 with no suppression versus signals with longer T2s. So the longer T2s stick around longer in this pulse sequence, but the short T2 decays really quickly. Whereas if we use a long T2 suppression, then we knock out all the longer T2s and we see nothing. So there is a problem with this approach of just using a long, low amplitude RF pulse, which is that a 20 millisecond rectangular RF pulse, has a very narrow bandwidth. It's about 1 over 20 milliseconds or 50 hertz. So that's super narrow, and it's much less than the B0 and homogeneity that we get across the body, even at 1.5 T, which is now considered to be a fairly low field strength. So a natural question is, can we use a different pulse with a higher bandwidth, that is, a shorter pulse? So first off, under reasonable assumptions, we can show that the mz at the end of the pulse is approximately equal to m naught times 1 minus T2 integral of the RF pulse. So this means that the decrease in mz is due only to T2 and RF power, right? So we can change either one of them to get knocked down mz. Now T2 is fixed, but we can increase power to get a shorter pulse. But the wider bandwidth pulse that we use with a higher power will also suppress the short T2s more due to Parseval's theorem. And we can see this by the following analysis. If we define omega 1 of t as the RF pulse and capital omega 1 of t to be the Fourier transform of that pulse, then the integral of the power of that pulse is the same whether you measure it in the time domain or the frequency domain. That's what Parseval's theorem says. So in order to minimize the suppression of short T2s, which is given by 1 minus T2 times the power of the pulse, we need to minimize this for the short T2 components, which is the same thing as minimizing the spectrum, the power in the spectral domain. So for long T2s, the excitation profile is Fourier transform of the RF pulse, which is given here, and this should equal pi over 2 in the suppression band that we care about. The suppression is then approximately 1 minus T2 times pi over 2 squared times B, and we need to minimize B, the strength of the, we need to minimize then B, the bandwidth. So this is a competing assumption, this is a competing effect, and it doesn't necessarily work so well to just increase the power of the pulse. And here's just a plot to finish off here. Here's just a plot of that approximation that we made for mz during the pulse versus the exact solution. So you can see that it holds fairly well for the short T2s relative to the duration of the pulse, but not very well for the longer components.